white and in red, you have the US. I don't know. There are seats over here. You can come down. There's a lot of thought there. Good morning, everyone. Welcome to today's colloquium. I met for the first time our speaker at an American Astronomical Society. In my previous job, I had to go to the winter AAS every year. And one of the most important parts of the AAS are the press releases. There are a lot of good scientific results that are presented there. At the press release, you might even know that in the US, actually everywhere in the world, some people strategize to get their results in parallel with the AAS, so they get a press release. So I was attending these press releases, and there was always a person that was always asking good questions. And that person was Ethan Siegel. And I know it was good questions, not because the questions occurred to me, because I don't know as much. He knows about absolutely every aspect of astronomy. And that was very clear to me at the AAS. And I knew it was good questions because how much the scientists presenting the results struggle to answer his questions. And I said, well, this person really knows about every aspect of astronomy. Then in the context of the Dickey's first light, I had time and opportunities to interact with him more closely. And ever since, we've been friends. And I decided that it was a good idea to bring him to get to know the observatories here on the Canary Islands. Ethan got a PhD in theoretical cosmology from the University of Florida. University of Florida, we have a lot of links with that university, and through that we share also common friends. After that, he went into a number of places in the US and universities. He was a postdoc in Arizona, in Tucson. He was at a number of US universities. But since 2018, I believe, he decided to be full-time a science writer. And he does write blogs on astrophysics. I follow him. I think these are the most informed blogs that you can follow in astronomy. He also has a podcast, Start with a Bang, that I also follow as much as my job lets me listen to the weekly podcast. Ethan really is a great pleasure to talk to him about astronomy. We've been a few days with him, and he's able to talk about every aspect of astronomy. I really mean it. He wrote a book on James Webb about what James Webb has done, and this is what this is going to be presenting today about the results of James Webb. I know you follow the mission quite closely. So Ethan, welcome to IC Colloquium and your time. Thank you.
Thank you, everyone, and thank you for having me here. Thank you for that lovely introduction, Valentin. And I do have to say, if you have bought and read my book, Infinite Cosmos, about the James Webb Space Telescope, you may be disappointed because I'm going to give you plenty of results here that have come out since that book came out, because the James Webb Space Telescope, as you know, it was launched in 2021, began science operations in 2022, And it's been taking science observations continuously since then and teaching us more and more and more about the universe as we continue to learn about it. You know, I was here, I flew in on Monday. On Tuesday, I got to go to La Palma, and I had one of the greatest experiences of my life. I got to go to the GTC, the Gran Telescopio Canarias, while it was observing. So in the dark, they let me into the dome, and if you've never been in a completely dark place at night, I encourage you to do it and let your eyes adapt to the dark, because for 5-10 minutes, we could see absolutely nothing, not even the hands in front of our face. And I had this idea. I said, oh, well, maybe if I put my phone on the floor and I let it take just a 30-second exposure, maybe it can see something. And it did. This is what it saw. And this is a spectacular view. You can, those of you who've been to GTC will recognize the assembly, the secondary mirror, and you know, if those of you who've seen the night sky probably recognize that too. But one of the things that struck me the most about this is what we can see is amazing, but very limited. At the same time, this is still very, very limited. Why? Because of Earth's atmosphere. Even if we could see every wavelength of light, not just visible light, but shorter wavelengths, including gamma rays, X-rays, and ultraviolet, we wouldn't see all of it because the Earth's atmosphere blocks all of the gamma rays, all of the X-rays, and most of the ultraviolet. And even if we could see longer wavelengths of light, we wouldn't see all of them because there are only certain windows in the infrared that make it down to Earth's surface at all. And pretty much none of the microwave, and only a little bit of, well, then you get to the radio and you say, okay, now we can see everything again. So you don't have to send radio telescopes to space. But that's the key, is if you go to space also, then in addition to everything you can do from the ground, there's also a tremendous amount of things you can do from space, because yeah, you can do radio from the ground, maybe a little microwave, a little infrared, and a little ultraviolet, and some good visible light stuff. But in space, nothing blocks anything. Everything, you can see exactly what's out there in the universe. So we do this. We have a mix of ground-based facilities and space-based facilities. And we want to cover everything because every different wavelength of light is sensitive to different astrophysical phenomena that are out there in the universe. If you want to see the highest energy boom explosions, you need to look for gamma rays because that's the highest energy light. If you want to see what happens when matter falls into black holes and poof, comes back out again, you want to look in X-rays. If you want to see where are the brightest, bluest, youngest, hottest stars forming, you want to look in the ultraviolet. If you know what you see in the visible light. I don't have to bore you with that. But if you want to look and see things that are cooler, that do not radiate, that even block visible light, you look in the infrared. And yes, at more distant things, you can see in the microwave and radio too. But this is what I love about astronomy, is that everyone has a place to contribute. Everyone who makes an observation in any of these wavelengths has unique knowledge to contribute. So this is a fun little example. This is a Bach globule. It's known as Barnard 68, and it's just a cloud of dust. If you spend too much time on social media, you may have seen this photo with the terrible, terrible caption, "There is a hole in the universe." No es un hueco universo. Yo prometo. It is not a hole in the universe, I promise. Because we can look at this in longer and longer and longer wavelengths of light. And when you do this, you see that, in fact, this is a cloud of gas, just a cloud of light blocking matter. Because at longer wavelengths, we learn something. Matter that blocks light is made up of dust. It's made up of actual little particles. If the wavelength of your light is short, is small, compared to the size of the dust will block it. The dust will absorb it and re-radiate it away in all directions, so you don't see starlight from behind. But if the wavelength of light is long compared to the little grain of dust, then it will pass right over it and the dust will not absorb it. So at longer wavelengths of light, many parts of the universe that are obscure will suddenly come into view. And that's not even taking into account the other thing that happens at long wavelengths of light. You can see visible light from objects that are farther away, because as the universe expands, which it does as time goes on, the wavelength of any light that travels through the universe gets stretched or redshifted. So if you want to see something that makes a visible light signature that's very far away in the expanding universe, you need infrared to go and see it. So we had an infrared space telescope. The flagship one that was launched was NASA's Spitzer mission, about a third the size of NASA's Hubble. Spitzer was a great mission. It taught us a lot about the universe, but only at low resolution and only for bright and nearby objects. Why? Because Spitzer is a small telescope. It only has a little bit of light gathering power, which is how much of the total light that comes in hits your telescope and you collect. So if you build a bigger one, first off, more wavelengths of light will fit across your telescope mirror, so you get higher resolution. Second off, you gather more light, so you can see fainter objects. You can see objects in more detail. And it also means with a bigger telescope, you can see objects with much less observing time. To collect the same amount of light between Spitzer and JWST, you would have to observe for almost 100 times as long with Spitzer just to collect as much light as JWST does. So there's pretty good motivation for it. From a more scientific perspective, though, you can look at, hey, of all of our space telescopes, Hubble, look at ground-based Gemini, look at atmosphere telescope Sophia, look at infrared space telescopes Spitzer and WISE, look at the ESA's Herschel mission, look at ground-based ALMA in the radio. These are world-class. These were the best facilities we had before JWST. Look how much better JWST is. Some places, it's about a factor of 10 better than Hubble. Some places, compared to Spitzer, like at 5 microns over here, it's factor of 100 better. And compared to something like WISE, factor of 1,000, even 10,000 better. So you can really discover a whole bunch of new things. Now, we build telescopes like this because we have science goals in mind. You can say, oh, if I want to see the farthest galaxy ever, then I want a powerful infrared telescope because it can see at these long wavelengths where the light is redshifted and it has a lot of light gathering power. So there are some, sure things. There are some certain things when we launched JWST, we knew it would break certain records. But we also build this telescope because we want to give ourselves the chance to surprise ourselves. When you build an instrument with new capabilities, when you look at the universe in a new, more powerful way compared to how you've ever looked at it before, you give yourself the opportunity that, hey, maybe there's something out there that we didn't even imagine, that maybe we didn't even think we could have imagined, because why would the universe do that? This is, for me, this is the reason why we do science. Not because we want to break this record or we want to know this detail. Yeah, we do. We do want to know those things. I don't want to downplay that, but I want to emphasize the biggest discoveries of all were the ones we didn't anticipate. For example, if you said, why did we build the Hubble Space Telescope? And why did we name it the Hubble Space Telescope? Edwin Hubble had been dead for over 30 years before they launched the Hubble Space Telescope. It wasn't named after Edwin Hubble. It was named after its mission, which was to measure the Hubble constant, to measure how fast the universe was expanding. It did that. That was the results of the Hubble Space Telescope Key project. It was released in 2001, and it was a big deal. Even in 2001, though, it was not the biggest discovery that was made with the Hubble Space Telescope. The biggest discovery was that the expansion of the universe was accelerating. This was done with ground-based telescopes in the 90s. Much of this critical data was gathered. But today, the overwhelming majority of these supernovae that confirm, that give us the details of how the universe expansion is accelerating, came from observations made with Hubble. So I want to keep this in mind as we go through this talk, that as we consider what can we do with this telescope, we are giving ourselves, every time we look at something, we're giving ourselves the opportunity to see what we've never seen before. And just maybe the universe will surprise us when we do that. So this is some pictures of JWST when it was on the ground. Over here is, you can see the sun shield being tensioned and tested. The mirrors are stowed and folded like they will be when they're in the rocket. This over here is a lights out test. That's what all the streaks with the technicians are. They are testing this with special UV lights to make sure that there are no fingerprints on the mirror, that everything is clean and pristine, that after they do vibration testing, that nothing has come loose or fallen out. It took some time, right? These images were taken, I think, 2018 and 2019. In 2020, I was very excited that launch was coming up. So I dressed up as the James Webb Space Telescope. This is real, I promise. I still have the mirrors at home. James Webb Space Telescope was not just a NASA US-based project. If you say who contributed to JWST, there are dozens of countries. I think around 40 countries contribute. I think about 200 member institutions from around the world contribute. So this is truly an international endeavor and an international observatory. It is joint between NASA, ESA, the Canadian Space Agency, and others. Contributions come from all over the world. Fun fact, when this telescope was launched, even though it was built in the United States, it was not launched in the United States. It was shipped from the United States to the French spaceport in French Guiana in South America by boat, guarded by the French Foreign Legion to protect it from pirates. In this day and age, still 16-day at sea, kept secret. The path was kept secret. The ship was guarded by the French Foreign Legion. It arrived in December of 2021 at the spaceport in French Guiana. And I don't know how many of you watched this launch, but where I lived, this launch happened at 4 o'clock in the morning on 25 December, on Christmas Day in 2021. It is the first time since I was a child that I woke up early on Christmas Day. And I did, and I watched this. And I'm not ashamed to admit that as the launch happened, they drew this line that was the trajectory the spacecraft was intending to follow. And you could see this yellow line, and you would hear the French word nominal ring out over and over again, because the green line of where the rocket was actually going traced out that yellow line perfectly. And you hear nominal, nominal, nominal. The first stage released of the rocket, the second stage continued, and then after the last nominal, release happened. And you could see they had equipped a camera on the end stage of the rocket. And this spacecraft moved away and started to separate. Now, what was supposed to happen is 5 minutes after separation, the solar panels were supposed to come out. And about 20 seconds after that spacecraft separated, I went, because I saw this. Just this, the solar panels started to come out. This is not a mistake. This would only happen because the spacecraft has sensors on board. And one of the sensors tells it, am I on the correct trajectory? If you're not on the correct trajectory, you have to wait until 5 minutes elapses and then the solar panels come on. But if you're on the perfect trajectory, the spacecraft says there is no need to wait. Automatically, I will deploy the solar panels, and it did. And we learned very quickly after that this meant because you have to use your fuel both to course correct to get you into the orbit you need to be at 1.5 million kilometers from Earth. But if you're already on the perfect trajectory, then you don't need to spend that fuel. So we were expecting that we would get 5.5 to 10 years of science out of JWST, because we expected we would need to use that fuel for the launch and to correct its trajectory. Instead, JWST is expected to operate for a total of 22 to 23 years. So everything that I will tell you today represents only the first 10% of JWST's science life. This was the first JWST image that ever came back. The very first image from JWST. Why are you not impressed? I'm just kidding. This doesn't look very impressive. Do you know what these points of lights are? They are all the same one star. JWST is made up of 18 mirror segments. And the first thing they did with this image was identify which mirror segment of the 18 segments did this correspond to. The things that say wing, these are the 3 left and the 3 right side mirrors that fold out. And the others are the 12 central mirrors, which is why they have a C next to some of them. So then they did course phasing, and they said, we're going to align these mirrors. And then they said, we're going to do fine phasing and align them so that they're focused more tightly. And then we are going to combine these aligned segments to make one single image. And this is what you got. And if you look closely, you can see that there's more than just one dot. There's like a faint dot over there and another faint one and another faint one, because they exposed this image for, you know, several hours worth of time. And when they did, and they put it all together, this is the image they released of what happened when the telescope was aligned. They were not expecting to get good science results out of this, but look at these backgrounds here. Except for that central star and the small star right there, everything else you see in this image is a galaxy. The alignment is so good that with its very first image, its very first test image, we said, oh my goodness, if we wanted to, we could do science with this right now. This is good enough data that you could do science with it. Some of you are going to look at these spikes and say, can't you get rid of those? Can't you make those spikes go away? And I'm sorry to tell you that no, you cannot, because these are part of JWST's design. If you had a perfect circle for a mirror with nothing blocking it, then yes, you would just see a perfect point source with, you know, diffraction limited, you know, rings. But we have a hexagon. So the 6 sides to the hexagon make 6 big spikes. The hexagons are actually tiles, so it's not a perfect shape. This shows up more at long wavelength, this fragmentation effect. The gaps, they're actually a very narrow effect. They barely show up. But those 3 struts that hold the secondary mirror in place, they show up very big at long wavelengths. So you will see at everything you get at least 8 points, 6 big spikes and 2 small spikes. In some places, some cases in the images, you will see something that looks more like this shape. We have a fun name for this in English. We call this the nightmare snowflake. And it shows up a lot in images. This is the completed full color version of the initial alignment mosaic. So you can see a bunch of stars, a bunch of galaxies, including galaxies extremely close to the star itself. This is great. It means just because something is almost overlapping with something else in our field of view, that does not stop us from observing it, from getting high quality observations with JWST. High resolution and very low noise and being in space allows you to do this. This was the image sharpness check. It was one of the last images that they took and composed before they said we are ready to start doing science. And then in July of 2022, the first science images were released. And there was a big press conference about it. And this image was very exciting. To me, it was extra exciting because I knew about this field of view. I knew it had already been imaged with the Hubble Space Telescope. This is Hubble's image of it. JWST, by the way, Hubble imaged this field for about 12 hours. JWST imaged this field for about 1/10 of that time. And this is what it saw. It was very exciting, right? You reveal so many details that are just not visible in the Hubble image. This is a fun little thing. When JWST looked not towards the center of the galaxy, but away from the center of the galaxy, it found these star-forming regions, and it found these jets coming out of the star-forming region. I think this is exciting because this was also imaged previously with Spitzer. Remember I told you we had an infrared space telescope before JWST? I want to show you the difference. Here is what Spitzer saw versus what JWST sees. Is this not an incredible difference? This is why you give yourself the opportunity to discover something new. You can see details that you would never have seen with the previous generation, no matter how long you observed. Being at high resolution is very important for science. This is also something that highlights the difference between JWST's different views. This is near infrared, this is mid infrared. And you can see different features show up at different wavelengths. Things that are warm gas, hot ejected material is good for near infrared. Things that are cold gas, regions that are collapsing, that's better for mid infrared. You recognize this image. This is the Ring Nebula. This is the Ring Nebula as seen by Hubble in visible light. You can look in near infrared with JWST, and you can look in mid-infrared with JWST. And as you go between these three views, again, you see completely different features. It gives you the opportunity to say, hey, if there's something in there that we haven't seen before, we can learn something new. Some of them will be things we expect, like knots of gas and dust. Some of them will be things we expected would be there, like the binary companion to the central star that's contracting in the Ring Nebula. But maybe some things will have the chance to surprise us. So we look at the pillars of creation. Now, this is just Hubble image. Hubble can do visible light, where these things are dark because they block the light. And Hubble can do near infrared, where just a little bit into the infrared, you can see through the pillars a little bit and see some of the stars forming inside. With JWST, though, this is mid-infrared and near-infrared. This near-infrared image is much more detailed than what Hubble can see, because Hubble can only go out to about 2 microns into the infrared. JWST can go to 5 microns in the infrared and all the way out to about 28 microns in the mid-infrared. So you can see things that no other observatory could have ever seen. We see more protostars inside. I love the one, you see the big pillar at the top, and then there's like a small, it looks like a face coming out of it. Look at the tip over there of the thing just above the face. You can't really see it in the near infrared, but in the mid infrared image, you can see there is a star in the tip of that. And that star was not yet known. So we are finding some of the youngest still forming stars in the universe, thanks to JWST. What is this? This is a galaxy cluster. And you see like, oh, that's a snake. It's eating the galaxy. Right? No, it's not a snake. That is a galaxy, one single galaxy that happens to be located behind this galaxy cluster, and its light is stretched, bent, and distorted by the gravity of the objects in front of it. These galaxies are shape distorted. That galaxy that looks like one of those light sticks that you shake back and forth, that's also one object being distorted by what we call gravitational lensing. This is very important. With gravitational lensing, we can see objects that are farther away that we would not be able to see if it weren't for the enhancement and magnification that these lenses or these gravity clumps make in the universe. So JWST can not only see farther, but we can look at these clusters to enhance its natural abilities with gravity, just natural enhancement due to the universe. This is a Hubble view of a spiral galaxy. And you say, well, what do I see if I look in near infrared? And instead of highlighting the stars, you highlight the dust and the gas and the new regions where stars will form. And then you say, well, what about in the mid-infrared? And this is the future stars. This is where the dust is still collapsing, where it will form stars in the future. So for me, this is hugely exciting, right? We're seeing the universe as we've never seen it before. The Hubble Ultra Deep Field is this image here. This is the longest exposed region of space ever. For 11 days, we made the Hubble Ultra Deep Field, and then a part of it that you can see up there, that's also JWST's field of view, has the Hubble Extreme Deep Field, which has 23 days of observing time. JWST looked at this for less than 1 day of total observing time, and it only looked at a part of it. And you can't really see how much better JWST is from Hubble than this. So I took a very small region right here. This is one version of the image. This is the Hubble version of the image. And now let's look at the JWST version of that image. Now this is exciting because you see different features, right? So I want you to look at a galaxy that looks pretty faint with Hubble. You see up there, there's a galaxy that looks like a blob, and then with JWST, it looks like you see those 6 spikes coming out of it. Those 6 spikes are not a star. That tells us there is a supermassive black hole in that galaxy that is active, that shines in mid-infrared light. We have discovered a huge abundance of active supermassive black holes with JWST. What you can see also, if you look very closely, is there are some locations where in the Hubble image, you don't see anything at all. Because what you are seeing, the light, Hubble cannot detect it. It's not at, Hubble can't reach the long wavelengths where the light is, but you can with JWST. Right? It's a bigger telescope. It's a colder telescope. It's designed to work farther into the infrared, so it can see this long wavelength light that Hubble cannot. And you say, well, if I can see longer wavelengths and I can resolve objects better and I can gather more light in less time, what can I find just by looking at the universe as I've never looked at it before? So has JWST broken any records? Yes. In this field of view was Hubble's record-breaking galaxy. Hubble had the record for most distant galaxy. It was called GNZ11. And it was the #1 most distant galaxy from when it was discovered in 2016 until JWST set a new record. The current record is this galaxy, Jade's GSZ140. You look at that. What does that phone number mean? What a weird thing. Jade's is the JWST Advanced Deep Extragalactic Survey. That's Jade's. And this was GS, the Galaxy Survey, at Z, of a redshift of 14, and 0, it was the first galaxy or the 0th galaxy found at that redshift. That's why it has that name. Now, you see there's a white part and a red part. That white part is not Jade's GSZ 14-0. That is a galaxy that is much closer. That galaxy is only at about a redshift of 2. But the red one is a separate galaxy behind it, because JWST doesn't just take color images, it also does spectroscopy, which means it takes the light from one of these objects, breaks it up into all of its individual wavelengths, and from the spectral signature, you can see things like the Lyman break. You can see things like absorption lines from hydrogen, from oxygen, and other elements. And in some rare cases, not this one, but some cases, you can even see emission lines when the galaxy gets excited, when the atoms in it get excited. So you can know exactly what redshift it's at, and you can measure the distance to it, and you can learn how early in the universe is this. Jade's Z14-0 is the #1 most distant galaxy. Its light comes to us from when the universe was just 285 million years old. Our universe is 13.8 billion years old today, which means this galaxy existed when the universe was just 2.1% of its current age. Some of you will be romantic for Hubble and you will say, what about GNZ11? Poor GNZ11, where are you now? The answer is not even in the top 10. GNZ11 is the number 11 most distant galaxy in the universe now. All 10 of the top 10 galaxies were either discovered or had their redshift measured and confirmed with JWST. So JWST owns all 10 of the top 10 most distant galaxies as of 2025. As time goes on, I expect GNZ11 to drop even further on the list. And that's only 430 million years after the Big Bang, or 3% of the universe's current age. What is this? This is a galaxy cluster. It is a famous galaxy cluster known as Pandora's cluster, or Abell 2744. And what do you see up there in those little boxes? These are very, very distant galaxies. Okay, so what? The reason we care is JWST measures their spectra, and 7 of these galaxies are all at the exact same redshift, the exact same very, very distant redshift. This is a very, very early stage galaxy cluster. It is the earliest. We can't even call it a cluster because it's still gravitationally collapsing. It is the earliest proto-cluster of galaxies we've ever found, and it breaks Hubble's old record by more than 200 million years in cosmic history. That's the kind of thing we knew JWST would be good at, and already it's broken that record. Has it broken any other records? Sure has. You recognize this maybe as a gravitational lens with a perfect alignment. It's called an Einstein ring. It's where you look out and there's a big, massive galaxy or galaxy cluster, and then behind that is another galaxy. And that galaxy's light gets bent, you know, even the parts that go up above, down below, to the left, to the right, they get bent back towards our line of sight. So that background galaxy gets stretched into a ring. And the foreground galaxy is the thing that is being the lens. It's making the gravity that bends the light. This is the most distant gravitational lens we've ever seen. The lens is 17 billion light years away. And then even farther away than that is the source. So JWST broke that record too. What are these things in those 3 circles? It is a single star, one star in a distant galaxy. The star is gravitationally lensed and is magnified by a factor of over 1,000. It is perfectly aligned. This is the most distant red supergiant star we've ever discovered. It is named Quyllur, Quyllur. I'm sorry, I have difficulty with that one. It's about 10 billion light years away, and it is the first red supergiant that we have ever seen outside of our local group. So we didn't just break the cosmic record, we shattered it by a factor of more than 1,000 in distance for this. First red supergiant star outside of the local group. We had seen active supermassive black holes as early as 670 million years after the Big Bang, before JWST. In 2023, the Sears collaboration broke that record. They found a more distant active supermassive black hole, less than 600 million years before the Big Bang. This, already less than 2 years later, this is now the number 3 most distant black hole, because we found UHZ1 even earlier. And then last year, JWST found an even more distant black hole, active, supermassive, in the center of a galaxy, galaxy GNZ11. So that galaxy has a new record now, the one that lost its old record. It used to be the most distant galaxy we know. Now it is the most distant galaxy with an active supermassive black hole that we know. And that record probably won't last for long either. And sometimes you find weird things. These you recognize, oh yeah, big galaxy cluster. And what's this yellow stretched thing with all these labels on it? These are arcs from galaxies and galaxy clusters that are behind the main cluster. They get gravitationally lensed, they create multiple images. And where you see SN2A, SN2B, SN2C, we saw a supernova go off in the lensed galaxy. And because the light gets bent by different amounts, it travels different distances before it reaches our eyes. So when a supernova goes off in that galaxy, we saw supernova 2A first. And then days later, we saw supernova 2B. And then several days later again, we saw supernova 2C. If your goal is to measure how fast the universe is expanding, a multiply lensed supernova is one of the most powerful tools you can have. So we're going to keep monitoring this system and other systems like it, because if we get a supernova again, this could help us figure out how fast is the universe actually expanding and how fast is the expansion actually accelerating. These are big controversial topics in astrophysics today, and JWST has the power to help us investigate them. This galaxy is also a nice surprise. This is the brightest, what we call emission line galaxy, the earliest emission line galaxy we've ever seen. We had seen emission line galaxies maybe 600 million years after the Big Bang, 580 million, 560 million. This one is 330 million years after the Big Bang. We do not know how you get rid of light blocking material so much that you can have, look at that spike in the spectrum. That's Lyman alpha at a redshift of 13.05. That's crazy. Except with JWST, it's easy. I can't emphasize enough how good JWST is. And yet, all of these things that I showed you, this is within the realm of, we expected JWST to be able to do this. We expected JWST to be able to find these things, to find earlier examples, more extreme examples, farther away examples, fainter examples of things we already knew about. But you might ask yourself, well, is there anything that was just a total surprise? Is there anything that we didn't even know that we should be looking out in the universe for this thing, and JWST showed us this thing that we didn't even think to imagine? I'm going to give you 5. These are my top 5. There are others, but JWST went and looked in the Orion Nebula. This is a JWST near-cam view of the Orion Nebula. This is the closest large star-forming region to Earth. It's about 1,300 light years away. It has thousands of new stars inside, and that's what it looks like to JWST's eyes. And you think, okay, if I'm looking in this region, this dusty star-forming region, I'm going to have substellar objects too, right? I'm not just going to have stars and brown dwarfs like the almost stars and planets. I'm also going to have things that haven't made it. I'm going to have these low mass protostars that aren't even brown dwarf mass yet. They may be still pulling matter into them, but they're just little clumps of mass right now that maybe they're still forming. And also, maybe because when I form stars, I get star clusters. And once those stars start forming, they radiate and they start blowing the matter away. So maybe I'll get these little clumps that were going to be protostars that were like, hey, I was pulling matter in. And what happened? Like, you got a bigger, brighter, more massive guy over there, and he blew all my gas away, and now I can't grow anymore. And I guess I'm just going to be a free-floating planet that never had a parent star. In English, we call these orphan planets because they are babies with no parents, right? It's very sad, right? Well, yeah, of course, JWST, it found them. You could see these little faint points of light with no bright stars around them, sad little orphan planets. But look, some of them where I have arrows pointing, there are actually 2 of them. These are between 3 and 7 times the mass of Jupiter. These are smaller than brown dwarfs. We call these jumbos because they are Jupiter mass binary objects. And surprisingly, they represent 9% of all of the free-floating planets we found in the Orion Nebula. We do not know how these formed. We did not expect to find them. No one had predicted them. Are they failed binary stars where it was maybe going to be a binary star and they just had all their mass blown away before they could finish forming? Were they ejected planets that came out in pairs when they were ejected from young stellar systems? We don't know. But these are questions that we didn't even know to ask before JWST because we did not imagine that these jumbos would exist. So that's surprise number 1. Then, oh, you recognize this. This is cluster Abell 2744. This is Pandora's cluster. Well, the good thing about JWST is it is not alone. JWST is up in space observing in the infrared, but we have other space observatories observing in other wavelengths. So we said, you know what would be interesting? Let's look in X-rays with the Chandra X-ray Observatory. That's our highest resolution X-ray observatory. And this is what Chandra saw. And yeah, okay, yeah, there's X-rays coming from that part of the galaxy cluster and X-rays coming from that part of the galaxy cluster. Because that's what happens when you have galaxy clusters. They heat up, they have gas, they collide, they emit X-rays. But look in that little box that's blown up here. You have a tiny, tiny, tiny galaxy in the middle with a white circle around it. That galaxy has only 10 million solar masses worth of stars within it. And over here in the X-rays, you could see it has an active black hole within it. Active supermassive black hole within it. From the X-rays, we can observe what is the mass of the supermassive black hole. And the answer is 9 million solar masses. I want you to think about those two numbers for a minute. We have 10 million solar masses worth of stars and a 9 million solar mass black hole. How do you get a supermassive black hole that is the same mass as all of the stars in the galaxy combined? Well, one thing that tells you is here's what it can't be. It can't be because, oh, we formed stars, and then the most massive stars died, and they made these little seeds of a black hole, and then they grew. You can only make a black hole that's about 0.1% of the stellar mass of your galaxy that way. That's what we see in the late universe. The most massive supermassive black holes are about 1/1000th of the stellar mass of a galaxy. But finding this black hole in this galaxy helps us answer the chicken versus the egg question. You know, what came first, the chicken or the egg? What came first in the galaxies, the stars or the supermassive black hole? This tells us that at the very least, some supermassive black holes must form independently of and separately from the stars around them. So we didn't even know to think, could these black holes have formed maybe from direct collapse, maybe primordially, but from some mechanism other than from stars. And now when we see things like this, JWST says, it teaches us, you have to look at this. You cannot make them from stars. That is a revolution. That's number two. This is not JWST. This was in 2017, we detected a gamma ray burst from this galaxy. Right, there it was. But also 1.7 seconds before the gamma ray burst came, we detected gravitational waves. This was our first kilonova event. It was a merger of two neutron stars, and it made what we call a short gamma ray burst. 30% of gamma ray bursts are short. They are less than 2 seconds. And 70% of gamma ray bursts are long. They last more than 2 seconds, but usually more like hundreds or thousands or tens of thousands of seconds. This was a short gamma ray burst. And so when we found this in 2017, we said, we know what short gamma ray bursts are now. They're merging neutron stars. Now we need to figure out what long gamma ray bursts are. And JWST said, okay, I'm here now. The next time you see a bright, long gamma ray burst, you call me and you make me point at it. And let's find out what'll be there. And it did. This was a long gamma ray burst, GRB 230307A. It is the second or third brightest long gamma ray burst of all time. And it went off in 2023. And JWST, well, it got what we call director's discretionary time. Said, this is important. Let's let JWST go look at the aftermath of this. And here's what it saw. What does this mean? We learned from these JWST observations, it was a kilonova. It produced the spectrum of heavy elements that we saw from GW 170817. This was merger of two neutron stars. That was not considered. People thought short gamma ray burst, well, long gamma ray burst has to be different. Maybe it's a superluminous supernova, maybe it's some other phenomenon, but it cannot be, right? Tidal disruption, shock breakout, cocooned supernova maybe. No, merging neutron stars. So now we are thinking, you know what? Maybe all gamma ray bursts are neutron star mergers. And what does that mean? Well, we don't know yet. We have to figure this out. This was a scenario we had not considered. That's surprise number 3. This is surprise number 4. These are called little red dot galaxies. This was not something people were expecting to see. And if you have heard a headline like JWST finds galaxies that break the universe, that no one could have expected, that this means cosmology is broken and in chaos and is over, and we have to go back to the drawing board, right? Maybe that's a little overblown, but these were headlines. It was because of these galaxies. We have theories for how galaxies form and grow up, and these galaxies all look bigger, brighter, and more massive than we would have expected from our picture of how structure forms in the universe. It turns out we had to find 4 separate contributions together in order to understand how these little red dot galaxies form. Step 1, JWST, when it saw how bright these are, we said, oh, this brightness means it's all stars. No. Immediately, we learned about half of that extra brightness is because JWST is optically overperforming over what it was designed to do. They designed it and they built it in a clean room. What we didn't realize is our clean room was cleaner than it ever had been for any other observatory. There was almost no dust or dirt or imperfections in the optics. So the telescope was collecting about 100% more useful light, about twice as much useful light as we were anticipating. So that was one factor. The second factor had to do with our simulations. We had made these big cosmic simulations at medium resolution and said, oh, we're going to get all the supermassive stuff out of there and we'll get the earliest galaxies. Well, guess what? If you want the earliest galaxies, you had better make sure to include the rarest, highest peaked overdensities. And so when we included that, when we accounted for that with a higher resolution simulation, things became much better. Then we said, oh, guess what? We had been assuming that we form stars continuously. And we don't form them continuously. They form in bursts. You make a burst of star formation, and then it quiets down. And then you get another burst. And so what we are seeing here is enhanced by bursty star formation. But the fourth factor, and Stephen Finkelstein would tell you this is the most important factor, is all of these little red dot galaxies also have an active supermassive black hole in them. And that is brightness enhancing them. So when we see these galaxies and we see the light, we have to ask ourselves, don't assume 100% of the light is coming from stars. Measure the galaxy and figure out how much of the light comes from the supermassive black hole. And then the rest is stars. And when you include all of those things, then at last, these little red dot galaxies make sense in the context of the universe. But we had to take all 4 of those steps. And this is one of those things that if you're an astronomer should bother you a little bit, right? Because this is how we do it. And I always am bothered by it, right? When you find things that don't line up, that don't match, you say, why doesn't it match? And you look for why doesn't it match? And if it still doesn't match, you keep looking. And then when it matches, you say, okay, now I stop looking. And is that really everything that's going on? We assume yes, but I would challenge you to keep that in mind as we move forward as astronomers, because even though we say this is solved now, there may still be more factors to disentangle, and we should not stop looking just because we got a satisfactory explanation. All right, and here's number 5. This is not a JWST image. This is just an illustration of our solar system. And you think, solar system, right. Any stellar system, it would make sense. It has some planets, and then it'll have what we call frost lines where, oh, this is the transition between when you can have solid ices, and if you're too close to the star, no more solid ices. And so where you have that, you should get an asteroid belt. And then you have more planets, and then you should have a Kuiper-like belt. And then out beyond that, you just have the faint Oort cloud that you can't see. So we said, well, with JWST, we have the power now to look at young stellar systems with dusty debris disks around them. And if we do this with JWST, we should be able to see the asteroid-like belts and the Kuiper-like belts in these other stellar systems. And so we said, oh, I know, the first one we should look at is Fomalhaut. It's only about 400 million years old. It has a famous debris disk that was seen by Hubble, and it's almost face on, like it's tilted so you can see the disk itself. Let's look at it and see if we can find the asteroid belt and the Kuiper belt. And we did, and more. It doesn't have two belts, it has three. It has an asteroid-like belt, a Kuiper-like belt, and an intermediate belt. No one knows what this is. Why is this there? What does it mean? Now we have to ask ourselves, oh, geez, are we even typical? We assumed every stellar system would have an asteroid belt and a Kuiper belt. Now we see three belts. Well, is two more common? Is three more common? Are there other options? Can you have four or more belts? Are there some systems out there with one belt? We don't know. But JWST said, oh, I can look at a second debris disk system because Vega is close enough and it's face on to us also. Here is the Vega system as seen by JWST. Do you notice that it is almost perfectly smooth? It sees no belts. It also sees no gaps in the disk. You could say, hey, wait, I think I see one, maybe at the edge of the white spot where it becomes yellow. There's one, like maybe that's a little gap. They have decided that even though Vega is more than twice the mass of the sun, the maximum mass any planet can be in this disk is only 40% of the mass of Neptune. It sees no belts and maybe one little planet. And that's it. So now we really don't know how many belts form in a typical stellar system. People are considering, well, maybe Vega is a fast rotating star, and maybe fast rotating stars suppress planet formation. But we truly don't know. These are questions we are only asking now because JWST has surprised us. We looked, we didn't know what we were going to see, and what we saw defied our expectations. And this is part of why we continue to build new observatories. This is why when you talk about space, you say, oh my goodness, we need a new X-ray telescope. We have not had a breakthrough X-ray telescope in more than 20 years. We need a far infrared telescope. The only space telescope we had to do far infrared in the whole 21st century was Herschel. And Herschel has been defunct for more than 15 years. It's why we say, oh, why do we not have a lunar radio telescope? If you build a radio telescope on the far side of the moon, that is the one place that is immune to all the radio interference mess we generate on Earth. So there is room to keep pushing the frontiers, both in space and also on the ground, as all of you know, because we would love to have a 30-meter telescope in the Northern Hemisphere. And La Palma is one of the two best sites on planet Earth for it. So we can be hopeful that that will come too. JWST has looked inside the Crab Nebula. This is not your familiar view of the Crab Nebula. You can see that it looks like there is smoke inside of it. This smoke that it sees are electrons being accelerated. This is low energy Thomson radiation being emitted from accelerated electrons in the Crab Nebula, discovered by JWST. This is the closest superstar cluster to us. It is 165,000 light years away in the Tarantula Nebula, and JWST has resolved it at higher resolution than anyone else ever has. We believe the single most massive star that we know of is in there, 260 times as massive as our own sun. And I would just encourage all of you to recognize that sometimes when you look out at the universe, you'll find unexpected things, like maybe somewhere in the universe, someone is looking back at us too. All right, and I'm going to stop here so we have a little time for questions. Thank you very much, everybody.
Thank you, Ethan. Really an excellent talk and exciting times to be an astronomer. Okay, so thanks for question. John.
It's not a question, but I want to mention Begoña Villa Costas, who studied here and was the right-hand person of John Mather, the scientific director of the Hubble Space Telescope. And you could see some of her work coming into practice. She was the chief engineer for all the test systems. And so as you're here, I thought it was worthwhile mentioning Begoña in this context. That's all I wanted to do.
And yes, she did a fantastic job. More questions? Okay, let's see if I get there.
One of the unexpected things JWST is doing is characterizing exoplanet atmospheres. Obviously, spectra don't have the same impact as images. Can you say something about that aspect of JWT's work?
Okay, we'll try this. So exoplanet spectra is something that JWST was indeed designed to do. It was, in fact, one of the first 5 science pieces that was released was the absorption spectrum of a giant exoplanet. So what JWST does is, this is one of the great things it does. It can do it both for direct imaging. If you can directly image your exoplanet, you can take a spectrum of it, but it can also do absorption spectroscopy. So if you have a star and you have a planet with an atmosphere that transits in front of the star, it won't just be the disk of the star that blocks light. You will also have filtered light through the atmosphere. This is the same type of light that shows up on the moon during a total lunar eclipse, right? During a total lunar eclipse, sunlight is blocked by the Earth from falling on the moon, but Earth's atmosphere makes a little ring that sunlight filters through, gets bent by, and can be detected. It lands on the moon. Well, exoplanets do this too. If you have an exoplanet with an atmosphere, the light will filter through the atmosphere and you will get absorption signatures. And depending on the strength and wavelength of the signature, you can detect what atoms or molecules are present in the atmosphere. Now, we have gotten a lot of claims that have been, oh, we found dimethyl sulfide in this atmosphere. Oh, we found this molecule that only life produces on Earth in its atmosphere. And you have to be very careful with this because, first off, you don't want to announce, we found alien life prematurely. That is 100% of the we found alien life announcements that have come out so far, including this recent exoplanet detection of dimethyl sulfide on an exoplanet. It's not even the first one. We had this claim on a Hycean world, K218b, earlier, just a few years ago. JWST should not be sensitive to detecting exoplanets of Earth size and below, to detecting those exo-Earth atmospheres. It can detect them for maybe Neptune-sized worlds and up, but what we really want to do that science, to do transit spectroscopy, is an observatory that is already designed called Habitable Worlds Observatory. That is what we really, really want to be able to get that contrast, to be able to see, because A sun-like star is pretty big, and an Earth-like planet is really small. The Earth blocks less than 0.01% of the sun's light, and Earth's atmosphere is only a tiny fraction of Earth. So if you want to get something that you can actually detect life or biosignatures like that on a rocky planet, you really need a superior observatory to that. And JWST, despite how good it is, that's still beyond its capabilities.
Okay, so I need to go up again. But it's good. You're gonna.
Hi, thanks very much. That was wow. So obviously, the James Webb is operating within an ecosystem of other facilities. How do we ensure as a community that things are not taken out of context and presented, extravagantly, even within the community? For example, you showed the red dots, whatever they're called. And that based on the James Webb data, we know that they have a supermassive black hole. There's strong bursts of star formation, which would imply that they should have been observed by ALMA, for example, but they're not. We've pointed with ALMA, we haven't seen them. So not the whole story comes from the James Webb side, right? So how can we make sure that before anything goes out, we actually have looked into all of its aspects, both within the community and mostly towards the public?
So that's a really good question, and thank you for that. This is something I've been struggling with for a very long time, and I'll be honest, I continue to struggle with it, right? Because one of the most popular types of headlines you will see in science news, it reads something like A says B, where A is some authoritative sounding name or collaboration or research institute, right? Harvard astronomer says, and then B is some untrue claim, is some claim that is not supported by the data. I die a little bit inside every time I read a headline like this because I never care what someone says, and I don't think you should care what someone says. I think we should all care about what is true, what is real. And as scientists, we often rush to be first. We rush to get our results out. We say we interpret it straightforward. We be as careful as we can, but we just publish what we have because it's time to get it out and put it in front of the community, and we'll move on to the next thing. Scientists, I think, aren't always concerned with what will the press say. I know, especially in my country, scientists often have the philosophy that any publicity is good publicity. And so more publicity, even if it's for untrue reasons, is better than less publicity. So you're always going to have people who seek this kind of attention. I think as a more senior person in the field now, I think it's up to us. It's up to the people who are, we're not the grad students, we're not the postdocs. If we're more advanced than that, it's up to us to say, hey, we need to be the voice of reason. We need to make sure that we are careful in our claims, because we know there are always going to be elements of the press that want to exaggerate, that want to make the extraordinary claim because they want the clicks and they want the eyeballs and they want the views. Don't make their job easy for them. Make the easy job being, we will tell you what is true to the best of our knowledge. I think that's what you can do as a scientist. There are some things that on the journalist side that we all can do better as well. But from a science perspective, if you're going to make a bold claim, make sure that your data can back up the bold claim, and that you're not just making a claim that 6 months from now, 1 year from now, 2 years from now, everyone who heard your claim is going to be misinformed, and they wind up thinking something stupid like, oh yeah, when the sun dies, maybe it won't even make a planetary nebula.
Well said. Okay, more questions? That's much easier.
Hi, thank you very much. I'm wondering about these long GRBs with kilonova association. Well, I didn't get how many of them has James Webb detected, if there is more than one or so, but I'm wondering, how long are these long GRBs, in the sense that, are they like in the lower duration end, like hundreds of seconds, or has James Webb also detected like a long GRB with a few hour afterglow duration?
Okay, so I would love to answer that question. So for long GRBs, like I said, 70% of them are 2 seconds or more. We only ever saw one long GRB that we were able to determine what made it, what created it. And it was the one I showed you. It's the only
It's the
one
only one.
that
Okay.
we know where did it come from. And the answer is that one long GRB was a little more than 200 seconds in duration. So 200 is a lot more than 2, but it's also, you know, 200 seconds is like, okay, like 3-4 minutes, right? It's not like this was 2 hours long, this was a week long. Some GRBs last a really long time, and this one wasn't like an extremely long, but it also was on the average side of like, yeah, long ones are average around here. So I wish we had more data that I could tell you about, but the way we determined it was kilonova is there were 3 heavy elements: selenium, tungsten, and I believe tellurium. These are elements that are not produced in supernova. These are elements that are not produced when you have colliding white dwarfs. These are not elements that are produced when you have core collapse explosions. These are not elements that are produced in tidal disruption events. They are only produced, as far as we know, in kilonova events, in neutron-star mergers. We think this is how you make the heaviest elements in the universe, and we see among the heaviest stable elements on the periodic table in this remnant. And so that's what JWST was able to do. It followed up 29 days after the GRB, and then again 61 days after the GRB. And it saw these signatures both times before they faded away. So I wish we had more data and I could give you a satisfying answer to your question, but I can only tell it, especially after the last question, I can only responsibly tell you what we know so far.
Thank you.
I think there is one online. Is that correct? Oh, was that?
You're welcome.
I actually do have one question, which is, and I've been thinking about this, but from a solar perspective, so I don't know much about it, but you've been showing how many supermassive black holes in different contexts and from different sources JWST has been finding. And then the question is, what are the deeper implications that supermassive black holes are more common than what we thought before JWST?
So I think the big implication for me is not that they're more common, right? We think that pretty much every massive galaxy has a supermassive black hole. And we found even in our own galaxy, we find globular clusters with intermediate mass black holes. They just announced Omega Centauri has an 8,200 solar mass black hole. So common is like, okay, like we think these things for about every galaxy, there's about one supermassive black hole. The real surprise is with the mass, because if you have what we call an overmassive black hole, which is a black hole that is too massive to be explained by the stellar population in the galaxy, it means you have to have some other mechanism, some independent mechanism for forming them. And the leading candidate is what we call direct collapse. So in simulations, right, we have to resort to simulations here. You say, well, what happens when you first start making structure in the universe after you make neutral atoms? So, right, you have the CMB, and then gravitational collapse starts really working well. And eventually you start forming stars and galaxies. But independent of that, about 100 million years after the Big Bang, what simulations give you is cold streams of gas that converge onto a point. And in simulations, you can actually get these cold streams, if they collide, to make these dense knots of about 10,000 to 40,000 solar masses. So the leading idea for where do these supermassive black holes come from is these colliding cold streams of gas, independent of any stars you make, will give you a seed black hole of maybe 10 to the 4, a few times 10 to the 4, maybe even 10 to the 5 solar masses. Whereas the first stars can only be maybe 10 to the 2 to 10 to the 3 solar masses. This is good because we believe we understand how black holes grow once you make them. It tells us that having a stellar mass black hole seed is too little. But if you go up by 2 orders of magnitude to these converging streams of cold gas, and then you have the galaxy grow and the black hole grow, that's how you can get that 1-to-1 ratio. You can get a supermassive black hole just as massive as all the stars combined in the galaxy. And we don't just see one overmassive black hole. We see plenty with a ratio of like 10%, 1%, much more than the 0.1% we see at late times today.
Understood. Okay. So Ethan is going to be with us today and tomorrow. Today, and help me here, Eva. So he has a meeting with the early career scientist students, postdoc at 12. Where is that? Oh, here. Okay. So, and then later there will be, yeah, you have a number of appointments, but probably there is still room if you want to talk to him. Tomorrow he'll come with us to Observatory del Teide, but in the afternoon he has also some appointments in case you want to talk to him. Send an email to Nieves. And with that, let's thank Ethan again for a great talk.